In this problem, we're trying to find the total solution for x1 and x2 based on these initial conditions and the spring constants and masses in the system. So we're trying to find what I will call x of t, where now x is going to be multidimensional. It's going to consist of x1 and x2. So I will spell it out explicitly here. We want both of these. All right, so still standard procedure, even though we're going to see in a minute that this is a 2 degree of freedom system. We are told for this example, using this generic picture here, we're going to ignore the damping. So C1, 2, and 3 are all going to be 0. So I'll just get rid of those from the picture. And we are not going to have forcing in the system. We are just going to give it some initial conditions and have the system go from there. So we have springs and we have masses and initial conditions only. So the modeling step, we are going to go to get our equivalent parameters, although the mass matrix we're going to find and the stiffness matrix we're going to find through the modeling step, through an energy approach using Lagrange's equations. And we're going to see, again, no damping because all the dampers are set to 0 for this example. So going back to starting with Lagrange's equations, we need to find the total kinetic energy, potential energy, and in general, Rayleigh dissipation, though here we'll see that that's just going to be 0. I'm going to start by looking at the total kinetic energy in the system. In this case, there are 2 objects that have kinetic energy, M1 and M2, and we can see here that they are constrained that each of them can only move horizontally, left or right. So, and they can't rotate. So linear kinetic energy for M1 and M2 is going to be present here. What is different than what we saw in anything we saw in Unit 1, where we were looking at these 1 degree of freedom systems, is that x1 and x2, the displacement of m1 and m2, are independent of each other. So because they are connected by this spring, this deformable spring K2, we can move m1 independently of m2. So for example, if we hold m1 still, so set x1 equal to 0, we can move m2. x2 can be non-zero. We can move it left and right, and that's okay. The spring is just going to expand or contract. Conversely, if we hold m2 still, so set x2 equal to 0, we can move m1 left and right, and it can freely move there. So x1 and x2 are 2 independent degrees of freedom, and it takes knowing both of them to fully describe the system. And just because we know the value of x1 does not automatically mean we know the value of x2. Unlike the 1 degree of freedom systems where all of the coordinates were just scalar multiples of each other, these two are independent. And that is going to come into play in having multiple equations of motion that make our system up. So in our kinetic energy, if we look at m1, it's going to be 1/2 its mass times its velocity. Velocities are always going to be absolute here, so it's going to be x1 dot squared. And then the second mass has a kinetic energy 1/2 mv squared. Its mass is m2, its velocity is x2 dot, and that gets squared. But here we don't have that coordinate transformation. We can't get x1 in terms of x2 through some scalar relationship or vice versa. We have to leave these as x1 and x2. So it takes those 2 independent variables, x1, x2, and that is all we can do for t. Now we can move on to v, the potential energy. In this case, k1, k2, k3 all will have potential energy. So let's look at k1. 1/2 times k1 times its deformation squared. So k1 on the left is attached to just the wall, 0. So it can't move, but the right side of k1 moves with x1. So whatever the value of x1 is, positive is going to be an expansion, negative will be a contraction, so it's just going to be x1 squared. Now, really what we can do, and we'll see why this is makes sense once we get to the K2, I can really express this as the relative displacement. It's just that the left-hand side is going to be 0. And then the right-hand side is x1. So x1 minus 0 quantity squared, that is just x1 squared. I'll rewrite that on the next line. Let's look at K3, since that will be similar. For K3, what is its deformation? Here on the right-hand side, it's stuck at 0, but on the left-hand side, that's going to move with x2. Now, since it's an energy and it's going to be squared, the sign, we'll see here, doesn't matter too much. But really what we can think about is what value of the left-hand side would cause it to be in tension, and what value on the right-hand side would cause it to be in tension as well. Now, for the K1, x1 positive is causing it to be in tension, and then the 0, positive or negative, it doesn't matter. Here, we could think about this as the left-hand side would be actually a negative x2, and on the right-hand side, a positive or a negative 0 is not going to matter. So I'm making this, it looks a little bit more complicated than what we've been seeing, but really it's exactly the same. But in 1 degree of freedom systems, we didn't have relative deformations. But where we do need to think about this is on K2. What is its energy? Well, it's going to be 1/2 times its spring constant times its net deformation. This is where now we have to be careful about the signs on the degrees of freedom. If we look on the left, it's attached to x1, and on the right, it's attached to x2. But for example, if x1 equals x2, since those are both measuring from an absolute position, if x1 and x2 are equal, there should be no energy in K2. It's not being stretched nor compressed. It's just purely translating to the right. So what we can think about here is really we need the difference between the two. And so that we get the signs correctly, let's think about the sign on each of them that would cause tension if the other degree of freedom were held at 0. So let's look at x2 first. So x2 being positive will cause tension if x1 is 0. So I'm going to put here a positive x2. Now for x1 being negative would cause K2 to go into tension when x2 is positive, is held at 0. So a negative x1. And it's an energy, it gets squared. So we did something similar in system dynamics when we were working with our free body diagrams and Newton's equations to get our equations of motion. This is going to be largely the same. So we have to be careful when both sides of a spring or a damper are going to be able to displace or have a non-zero velocity. It's not a big deal with K1 and K3 since one side of it is 0, so we don't have to be quite as careful because the quantity is going to be squared. But here we need that x2 minus x1, or we could have had x1 minus x2 would have been all right also. We can't have x2 plus x1 based on how the degrees of freedom were defined, where x2 right positive, x1 right positive. And just to make sure this works, again, if x2 and x1 were equal, K2 translates, x2 minus x1 would be 0, and we would see no energy in the spring, either compression or tension. So we can rewrite V now. This is the way we would have seen it before. Right, so notice that's just x2 squared because that negative is going to go away anyway when we square it, plus K2. And here I will do the FOIL, or I'll do the difference of squares. So x2 minus 2x1 x2 plus x1. And that will be squared and squared. Right, so I did multiply that out so that when I do the differentiation step in a moment, it's going to be easier to deal with. And the R, just for good measure, R is going to be 0. There's no dissipation in the system as we're looking at it. We're saying all the dampers are set to 0. So we have potential and we have kinetic energy only, and there's no forcing. Now I want to go further, and I want to use Lagrange's equation because that's going to be how we go from the modeling step to the equation of motion step. In general, we'll have this d dt times partial t partial xi dot. And that'll be a minus del t del xi, which will usually be 0, and in this case it will be, plus a del r del xi dot, plus a del v del xi equals, and there's no forcing, so the right-hand side is going to be 0. That is the most general way we're going to see this. In this problem, r is 0, so that term goes away, and there are no displacement terms in the t, only velocities, so that second term will go away as well. Now notice here, unlike what we saw in Unit 1, I have x dot sub I, x sub I, because I'm going to do my Lagrange equations twice. I have to do it for each independent degree of freedom. In this case, x1 is my first degree of freedom and x2 is my second. So I need to take, for my first one, I'll write it out in long form here, del t del x1 dot plus del v del x1 equals 0. All right, so then now it's a scalar equation because I'm doing it for specifically x1 first. So let's see what pops out here. And there'll be kind of overlap between the modeling step and the equation of motion, as we'll see in a moment. So let's take dt del t del x1 dot. So looking up at t, I am going to get m1 x1 dot. So the 2 and the 1/2 are going to cancel each other. Now I'm going to take the time derivative of this, so the x dot goes to x double dot. Now, plus del v del x1. So go down to the v, the second one that we wrote. So if I take the partial of this with respect to x1, I'm going to get, well, the first term, the 2 is going to drop down, and I will be left with k1 x1. On the second term, I have no x1, so that will go away when I do the partial differentiation. Now here I have this 1/2 k2 x2 squared. That will go away. I will have a minus 2 times 1/2 is 0. I will have a k2 x2 plus, when I differentiate the x1 squared term, the 2 and the 1/2 is going to cancel, k2 x1. Right, so what we want to really look at here is this mixed x1, x2 that came out from the difference of squares when we do the partial differentiation on that. So in this case, I differentiate it with respect to x1. Well, the x1 dropped out because it was x1 to the first. That just goes to 1, and I'm left with the x2. And now we're going to see something similar when I get the second equation of motion. So actually, let me rewrite this briefly. So I want to rewrite with grouping together my variables. So notice I have an x1 and another x1. I want to group those together. So I'm going to factor the x1 out, minus, and I have a k2 x2, and this equals 0 equals 0. So this is actually my first equation of motion, but I'll write it in a matrix form for the equation of motion step. My second, I'm going to do what I just did, but everything will be partially differentiated with respect to x2. So going up to t, the first term drops out. There's no x2 term. Again, it's a partial derivative. And then the second term is going to leave me with m2 x2 double dot. Now I'll go down to my v. The first term, 1/2 k1 x1 squared, that drops away. There's no x2. Then I'm going to have my next term is x3 x2 after I partially differentiate with respect to x2, plus I'll have a k2 x2 from that first term. Now the mixed term is going to give me a negative k2 x1. And then the third term, that x1 squared, that drops out. and then my right-hand side is 0. And that's what I get from applying my Lagrange equation the second time, but now differentiating with respect to x2 and x2 dot. Right, so two equations of motion we already have, but I want to write it now in matrix form. So what I am going to do is I want it in the form of mx double dot plus kx equals 0, where x is going to be x1, x2. So kind of like how we write state space form, but this is not the state space form. x1 is a position and x2 is a position. This will be compatible with state space form later, but that's not what this is yet. All right, so I'm going to take these two equations and just write them as one matrix equation. I know that my M matrix is going to be 2 by 2 because I have 2 degrees of freedom. And that will get multiplied by x double dot plus k is also going to be 2 by 2 multiplied by x equals 0. And actually, I'll rewrite this the same way I wrote the first one. I'm going to group my variables together. So in this case, these both have an x2. So I want to group their coefficients, k2 plus k3, x2 equals 0. This will make the writing of the mass and the stiffness matrices easier. All right, so let's fill in the details for the mass matrix. So what we do is we're going to go equation by equation. I'll go with equation 1 is going to be my first row. So just as a note here, that's how the first row is going to get filled in. I'm really just rewriting it, but in a matrix form. So equation 1 is filling in this row. So equation 1, I have an m1 times an x1 double dot plus, now it's not written here, but 0, I have to explicitly write in the matrix here, this first equation has 0 times x2 double dot. Right, that's accounted for. Now I get to my stiffness matrix. What's my coefficient in front of x1? It goes in this cell, k1 plus k2. And then my coefficient in front of x2, negative k2. And then the right-hand side is 0. So I'm done with the first row of this matrix equation. So again, I've already written everything. It's just putting it into this format for the equation of motion is what I want to do. Now, the second row of my matrix equation, I am looking at equation number 2 as I rewrote it in the second part. So what's the coefficient in front of x1 double dot? Well, in equation 2, that's 0. And then m2 is the coefficient in front of x2 double dot. Moving over to the x1 and x2 terms, I have a coefficient of negative k2, and then a coefficient of k2 plus k3 in front of the x2. Right, so I now have my M matrix and my K matrix. The M matrix is this diagonal matrix of M1 and M2, and then the K matrix is this mixture over here. So I'll label them again just so it's very clear. M matrix, K matrix. And now I can fill in the values that we were given. So I also will put it numerically here in the equation of motion. So we were told that M1 is 10, M2 is 1 kilograms is the base unit. K1, 30 newtons per meter, 5 newtons per meter, 10 newtons per meter for 2 and 3, again, in base units. So just plugging in the given values here, we get that the M matrix can be written as 10, 0, 0, 1. And the K matrix will be 35, negative 5, negative 5, and 15. So expressed numerically and in variable form. Always start in the variable form and then go into the numeric form. Now, before we exit this equation of motion step, we want to check, are all of our matrices, the mass, the stiffness, and damping if we have it, are they symmetric? Because if they're not, we did something wrong in these linear systems. So checking M, we can check the variable form, or we can check the numerical form. Both will give us the same result. If we look at M, well, it's a diagonal matrix, so the off diagonals are 0 and 0. So yes, M is symmetric. It's symmetric if the off diagonals in corresponding places are equal, is our general definition of a symmetric matrix. If we look at K, we don't look at the main diagonal, doesn't matter, but the two off diagonals are both negative K, 2, or numerically negative 5. So yes, K is also a symmetric matrix. So that's a good first check before we go further in our problem to test our modeling. So we have our equation of motion written in this form, this matrix form. So now we can go to our identify step. And we'll look at our equation of motion and we will identify it, classify it so that we know what the solution is going to look like. Now, different than what we saw in anything in Unit 1, we have 2 degrees of freedom, x1 and x2, 2 independent degrees of freedom. So we're going to identify 2 DOF system. It is linear, and we know that because we're able to write it in this matrix form. If we can't put it into this nice constant matrices of M and K, like we have here, M1, M2, K1, 2, 3, those are all constants. So this is still linear. It is undamped, and it is also free. So undamped or no dissipation mean the same thing. The right-hand side, there is no forcing, so it's free or autonomous, however we want to express it that way. With the identify step complete, now with it fully identified, let's look at what the general solution looks like. So x of t, this is again as a vector since it's x1 and x2, will be in the form for a system in this format, c1 chi1 cosine omega 1t plus phi 1 plus c2 chi 2 cosine omega 2t plus phi 2. So the general solution for this, there's no dissipation, so there's no steady state solution per se. This doesn't decay, it doesn't die out. It's going to keep oscillating at the 2 natural frequencies, omega 1 and omega 2. Now, there'll be different phases, phi 1 and phi 2, and it'll happen with different amplitudes, which we'll get from the C1 and chi 1 combination and the C2 and chi 2 combination. But this is what the solution is going to look like. We need to figure out these parameters. So let's start with finding our natural frequencies. Natural frequencies are going to come from, and we could have done this in 1 degree of freedom, but we can just use the root k over m. But for 2 degrees of freedom, and as we'll see for higher dimensions, this is going to come from, this is going to influence it. We need to find the eigenvalues of m inverse k. So the M matrix and the K matrix, the eigenvalues are what we're going to use to find the natural frequencies. The natural frequencies are actually the square root of those eigenvalues. So I'm going to do this in MATLAB. I'm not going to try to invert matrices by hand or find eigenvalues by hand. For 2x2, it's possible. It's not too bad. But once we get to higher dimensional systems, we certainly don't want to do that. So we'll jump into MATLAB, get our parameters, and then put it back together by hand before we go into plotting. In MATLAB, I will put in my values for the K's and the M's, and then the M and the K matrix. And just to check, our M and our K are both correct. I'll hold off on the eigenvectors for the moment. I'll come back to those, but let's look at what I'm doing at 16 here. I'm doing M \k. Now, on paper, What are we doing? We're doing m inverse times k, which in MATLAB I can use inv_m for inverse of m times k. And that is the answer I get. That's the matrix, 3.5, negative 0.5, negative 5, 15. And for 2x2 systems, that's fine. But if we're using MATLAB, a quicker way to do exactly the same thing is m\k. And notice we get the exact same result. However, MATLAB is much more efficient with the backslash operator than the inv to actually invert the matrix. So I won't get too much into it, but it uses a Gauss-Jordan elimination, which it can do faster than actually inverting m and then multiplying it. It's able to do the operation we actually want to do as one step. So for higher order systems, this is much more efficient. But m\k is going to be equivalent for the most part to this command where I actually invert m and then multiply it by k. So that's why in line 16, I'm doing m\k. It's doing mostly the same thing. Now, if I just get the eigenvalues from this, I'll run just this little piece. We see that we get 3.29 and we get 15.2. So those are the eigenvalues of m inverse k. The natural frequencies of the system are the square roots of these eigenvalues. So for right now, I'll just do it in the command window. I'll automate it in a second here. So I want the square root of those values. Those are the natural frequencies of my system. I have 2 because I have 2 degrees of freedom. So I have natural frequencies of 1.81 and 3.90. Notice it did give them to me in ascending order. That's not always the case. But on paper, when I record these, I would always put them in ascending order. So we'll go back and we'll record these values. Right, so in order, we have 1.81 and we have 3.90 with only keeping 3 digits here. I'll get rid of this since we did it all in MATLAB, but that's where it came from. Radians per second. So notice I recorded them in ascending order, and that was the normal order that it came out for this problem in MATLAB. However, out of MATLAB, sometimes they are not in ascending order, in which case we're going to need to sort them. All right, so those are the 2 natural frequencies, omega 1 and omega 2. Now we can get our mode shapes, chi1 and chi2. Right, so I'll just call it chi for the moment because we're going to see how MATLAB delivers them to us. So with the same command, this eig command, we're going to get both the eigenvectors and those eigenvalues that we actually already found. So let me run up to here and we can see what we get. L, that second argument out of eig actually finds what we call the eigensystem, which is the eigenvectors and then the eigenvalues. So the L coming out on the left-hand side is a diagonal matrix of my eigenvalues. This is exactly what we just found. V is my eigenvectors. And we see that V is actually a 2x2 matrix. It is containing both of the eigenvectors. And if we look at the arrangement, this L, this first value up here, the 3.28, which then we take the square root and it's the 1.81, that is associated with the first column of V. So the first column of V is the first eigenvector associated with the first natural frequency as it comes out of MATLAB. We might need to rearrange it to put it in ascending order. Now, the second eigenvalue, the 15.2, which gave us the second natural frequency of 3.9, that is associated with the second column of V. So the 0.0426 and the negative 0.9991. Now, the way that MATLAB delivers eigenvectors, each column has a magnitude of 1. That is how it normalizes it. That is how it scales it. And we'll look in a minute at a difference at how Mathematica would do it. But I'll record these values out of MATLAB as we go. So the first column is my first eigenvector. The second column is my second eigenvector. So I'll transcribe these. So for the chi1, and there'll be a little bit of rounding here, I got negative 0.920 and negative 0.393. And for chi2, again, there'll be rounding here, is 0.0926, and I'll write as negative 1, even though clearly this can't have a magnitude of 1, but with rounding, it's very, very close. So yeah, I want to point out the first natural frequency, 1.81, is associated with chi1. The second natural frequency, 3.9, is associated with chi2, and that's important for when we construct our solution at the end. Chi1 and omega 1 have to be together, and chi2 and omega 2 have to be together. Now, I want to show just the difference if we do this in Mathematica. We can if we want to do it. I've established my M and my K matrices here, and I want to do the same operations I was doing in MATLAB. Well, it's a little bit different in Mathematica. So here, there's other ways to do it, but the way I'm doing it here, I am doing M inverse times K, because that is and I'm going to call that matrix MK. Now notice in Mathematica that I'm using the dot to multiply M inverse times and K together. In Mathematica, the dot actually does the matrix multiplication, which is what I do want to do in this case. The asterisk or the times just does the element-wise. So it's a little bit reverse of how MATLAB does it, where a dot multiply in MATLAB is element-wise, whereas just an asterisk is going to be a matrix multiplication. So I do want the matrix multiplication here, and I do that. So MK is M inverse times K. Now, in Mathematica, I can get the eigenvalues using eigenvalues. And we see that those do match the eigenvalues that we got in MATLAB, and they should. They're just in this case, descending order, but we can always reorder them if we want to. And then we can use the eigenvectors command to get our eigenvectors. So notice we definitely do get a different answer here. And it comes out in a weird way compared to MATLAB. So this 15.2 eigenvalue is associated with actually this first row that comes out when we express it in matrix form. And this actually looks pretty much the same actually as what MATLAB had, because the value of the second part of it was 1. However, for the other eigenvalue, the 3.29, this is the eigenvector associated with it. And it does look a lot different than what we saw with MATLAB. The way that Mathematica likes to express eigenvectors, you'll see that it likes a 1 as the second, or in general, the last value. So it just rescales how MATLAB did it. So it is the same eigenvector, it's just scaled differently than what MATLAB had for us. And also, it's outputting these as rows instead of columns. So typically, I would recommend using MATLAB, but if you're going to use Mathematica, just be aware of these differences in how it is expressing the eigenvalues and the associated eigenvectors. But back to what we were doing by hand, again, keeping just the outputs from MATLAB. So these are the chi1 and chi2 I'm going to use. Again, if we use the differently scaled ones out of Mathematica, that's fine. It's not wrong as long as the ratio between all the values in the eigenvector are the same. We can still end up with the same final answer, because our C1 and our C2 would be different if we had a different chi1 and chi2. So when we apply the initial conditions, that's where the product of C1 and chi1 is always the same, and the product of C2 chi2 are always the same, even if we got different scales of eigenvectors. Now, we still need C1, we still need phi1, C2, and phi2 in our parameter step. And to get those, we are going to need to apply our initial conditions. So I'll put a placeholder here, since that's what we want to do next. Apply initial conditions and solve for these remaining parameters. So we are told to use, going all the way back here, the initial position on x1 is 0.1 meters, so 0.1 to the right. x1 of 0 equals 0.1. All other initial conditions are just going to be 0. We're going to put these initial conditions into our vector here. So we want x of t, although we want this at 0, is going to be 0.10. So this is a vector expression. Is c1 chi1, we know chi1, we know that vector already, cosine omega 1, which we know, times t, so that actually will go to 0, so that's just cosine of phi1, plus c2 chi2, we already know chi2, cosine of phi2. So this is actually 2 algebraic expressions that we need to solve, and then the other 2 are going to come from x dot of 0 will be, in this case 0, 0, will be negative omega 1 c1 chi1. Omega 1 and chi1 we already know, times the sine of phi1, plus a negative omega 2 c2 chi2 sine of phi2. So these are the 4 equations we need to solve simultaneously in order to find our 4 unknowns, c1, c2, phi1, and phi2. And I'm going to rearrange this a little bit because to solve these 4 algebraic expressions, we're going to use fminsearch like we did in a previous example. So what I can actually do here is I'm going to subtract this 0.1 off of this side so that this is going to be 0. And I'll do the same thing down here. Now here it's really not doing anything because I'm just subtracting zeros, but this is the general form that I want because this is the 4 equations I need to solve simultaneously in that fminsearch. And we'll see how that's applied in MATLAB. Going into MATLAB, I am defining those 4 equations here, what I'm calling x1, x2, x1 dot, x2 dot. So these are the general equations, and then I will solve them at 0, at t equals 0. So these are just defining the 4 equations I just used, and then I'm defining my initial conditions. Again, 0.1 for x1, 0, and all the rest are going to be 0. So 22 through 25 define my xt and x dot t, and my initial conditions are defined here. So I'll just run up to this point again. Now, what am I doing with these? In an fminsearch, and that's what I'm going to be doing down here in 35 to 41, I want all of these functions to be 0. So I'm doing an fminsearch on the norm of these 4 functions. Again, kind of in a similar way to how I did this before. The minimum will occur when each row, 36, 7, 8, and 9, is equal to 0, and each row can only be 0 if the function evaluated at time equals 0 is equal to the initial condition. So that when this is minimized, it's at least very close to satisfying all 4 of those conditions. Now pay attention to the particular way I'm defining my x1 here. I'm making a function of 2 variables, time and c. C is all 4 of my coefficients. C of 1 is c1, c of 3 is phi1, c of 2 is c2, and c of 4 is my phi2. So I'm just mapping them to c1, 2, 3, 4 because that's how fminsearch is going to operate. So notice here, it's going to be trying different values in that c vector until this expression is minimized, and the minimum of it should be 0. Now I'm going to put some options in here when I do my minimization. I'm making the tolerances lower than normal and the iterations higher than normal. So tall x defaults to, I think, 1 times 10 to the negative 6. I'm making it much smaller. The function tolerance also much smaller, and more evaluations, more iterations, just to make sure I'm going to find a good value when I do my minimization. And finally, I am going to give it some initial guesses. I don't know what C1, C2, Phi1, and Phi2 should be, So I'm just going to make it something kind of random to start. I'm actually using a rand here to make sure I don't, it's not always good to pick like integer values or pi over 2 or 0. So I'm just going to, if I run this, this is going to be my initial guesses. So I'm just going to guess at first that C1 is negative 0.8, C2 is negative 0.44, phi1 is 0.009, and phi2 is 0.09. But every time I run this, it'll be a little bit different. And that's okay, because I'm going to see what happens. All right, let me run this section here. All right, so notice my outputs from the fminsearch, I'm getting C, I'm getting this little F, flag, and output. The F and the flag are going to be important to make sure that the C I'm getting is reasonable, hopefully. So let's see what C I got. This is the collection of C1, C2, phi1, and phi2 that it used to minimize this expression. Right? So negative 0.107 about for C1, 0.042 for C2, and then phi1 and phi2 are both 0. And that'll be typical when our velocities are initially 0. But let's check F. F is the value of the function when minimized. So that is what is the norm of what is this when it gave up. Ideally, it should be 0. That means that everything was exactly satisfied. We're getting 8 times 10 to the negative 14. That's really small. That's basically 0. It will never be able to, with absolute precision, get us to 0. And then flag, we want to see a 1 there. That means that the solution converged. So if the value of the function is very, very small, very close to 0, and it converged, then this C collection we got, we can probably trust. So applying our initial conditions for this scale of chi1 and chi2, we get that the C1 value is a negative 0.107, C2 was a positive 0.042, and our phi1 and phi2 were both 0 radians. Now, once again, if our chi2 and chi1 were scaled differently, like we used the one out of Mathematica, we would get different C1 and C2. But when we assemble this, their products would be the same no matter what the original scale of chi1 and chi2 were. So now we can assemble our solution. Putting together our xt equals. All right, so let's see what we have here. We have our C1, C2, chi1, and chi2. So I'm going to take their product and put it in front of cosine. So C1 times chi1, I will get 0.0982 and 0.0419. Okay, so again, I'll just take a note here. This is C1 chi1 times the cosine of omega 1, the first natural frequency, which is the smaller one, times t, minus phi. Well, both of those phis were 0. Plus, now this is going to be C2 chi2, 0.0018 and negative 0.0419. Again, that's the product of C2 and chi2. And that's going to be multiplied by the cosine of omega 2 times t minus phi2, which again, from applying initial conditions, we found that the phi1, phi2 were both 0. Right, so no matter what chi1, chi2 scale we found, this is what we should be getting for our total solution once we multiply everything out and apply our initial conditions, where the top row is x1 and the bottom row is our x2. So it's just written in this vector form, but that is our solution. So let's take this and plot it. What does x1 and x2 look like? So we can just put it all together here in the code. Now that I know x1 and x2, now that I've discovered those constants c1, c2, and phi1 and phi2, I can feed those back into these definitions up here for x12, x1 dot, and x2 dot, although we only care about x1 and x2 here. But I can put in those specific values for c, and that's what I'm going to be doing down when I do my plotting. That's where I put the capital C in. That's the output from my fminsearch. So running this and making our plot, this is what we get for the behavior of x1 and x2. Now note that they're oscillating at two frequencies, which are the two natural frequencies, but with different amplitudes. So what's happening to x1? x1 looks mostly like it's oscillating at one amplitude and then a little bit at the second amplitude, but it looks more or less like a single cosine, whereas x2 is clearly oscillating at these two or multiple frequencies. So that has to do with the relative amplitude, at least, on the first cosine term versus the second cosine term. So if we notice the first row of x, which is x1, the coefficient in front of the smaller natural frequency is much larger than the coefficient in front of the second term. So that's why it appears that it's mostly oscillating at the 1.82 radians per second and barely any at the 3.9. However, for x2, the second row, their coefficients are actually the same in front of the two frequencies. So that's why there's a noticeable oscillation at both of those frequencies when we plot it. So as the time trajectory, that's what we're seeing, but let's visualize it also in animation. So here I have x1 is the red square and x2 is the blue square. And I just put it so that they were 1 meter apart just so we could visualize how they are oscillating together. So notice that they are oscillating the red one mostly just back and forth in that cosine, and blue has a more complicated looking oscillation pattern that it is exhibiting. And I'll run it one more time so we can see those oscillations happening. So again, x just basically going back and forth, and the blue one has a more complicated trajectory. So putting everything together here, we first had to model our system using Lagrange equations here, having two independent degrees of freedom. So we got two equations of motion when we differentiated with respect to our first degree of freedom and then again with respect to our second. These two scalar equations of motion I then combined into one matrix form of equation of motion so that I could identify my mass matrix and my stiffness matrix, M and K. From the equation of motion, I could identify it as having 2 degrees of freedom, being undamped, and having free vibrations, and we know then what the general solution should look like. Then we can find our parameters. The natural frequency and the mode shapes come from taking the eigensystem of M inverse times K. So that's why we need the matrix form of M and K to get those values. The constants, C1, phi1, C2, and phi2, those come when we apply our initial conditions and in this case solve 4 simultaneous algebraic expressions, and then we can figure out what the C's and what the phis are. And for this one we got that the phis were 0, there was no phase, and we got the values of C1 and C2. Now we can assemble our full solution by multiplying out the C1 and the chi1, the C2 and the chi2, putting in our natural frequencies, and in this case 0 phase, but the phase would go into those cosine terms anyway. And this is what we get the vector equation for our 2 degrees of freedom, x1 and x2.